We are moving on to the next section, section 1.2, some preliminaries. So here in this section, we will be discussing about the preliminaries required to start our course. And most of these preliminaries have been discussed in your previous classes. The first one being sets. You know that a set is a collection of or a well-defined collection of objects, and those objects we call by the name elements of the set. We know that sets are represented by capital letters, okay, A, B, C, etc. Now, suppose A is any set and X is an element of that set. Then we write X element of A. And if X is not an element of A, we do not like this. X not element of A. Now, if you're given two sets A and B, then the union of these two sets, A union B, is defined as X is a member of A union B. X belongs to A union B, or X element of A union B, if X is an element of A, or X is an element of B, or X is an element of both A and B. Then the intersection between these two sets A and B is denoted by A intersection B, and it is defined by the rule X is an element of A intersection B if X is in A and X is in B. Now we have the following standard notations for the sets. Set of natural numbers is denoted as N, set of integers denoted by Z, set of rational numbers denoted as Q, set of irrational numbers denoted as I, and set of real numbers denoted as R. Now we shall see the different ways of representing sets. The first way of representing set is by listing the elements in the set. For example, the set of natural numbers denoted as N is defined as set N is equal to set 1, 2, 3, 4, etc. Just listing the natural numbers. Now, another way is to represent a set is by describing in words. For example, the set 2, 4, 6, 8, etc. That means the even numbers or even natural numbers. We just say that it is a set of even natural numbers or collection of even natural numbers, and that set is denoted as E. Now, another way of representing a set is by using a rule to define the elements of the set. For example, S is equal to set of all R element of Q. Q means a set of rational numbers, such that R square is less than 2. That means this set contains all the rational numbers whose square is less than 2. So if you look at 1 square will be less, 1 square is 1, which is less than 2. So 1 will be an element of this set. Now if you look at 4 by 3, 4 by 3 the whole square, 4 by 3 the whole square is 16 by 9. 16 by 9 is clearly less than 2, so 4 by 3 will be an element of this set. And if you look at 3 by 2, 3 by 2 the whole square is 9 by 4, and 9 by 4 is greater than 2, so 3 by 2 will not be an element of this set. Okay. Now with these notations or with these sets N, E and S, we are going to look at some things here. N union E. N is a set of natural numbers and E is a collection of all even natural numbers. So N union E will be clearly N, and N intersection E will be clearly E. Now S, look at S. The only natural number which will be in S is 1. So N intersection S will be the singleton set 1, and E is a set of even natural numbers, and S is a set of all rational numbers whose square is less than 2. So we can see that E and S does not have any elements in common, so we write E intersection S is equal to phi. You know that phi is the empty set, that means the set without any elements. We also call it as the null set. Now if the intersection of two sets as we see here, intersection of E and S is 5. If the intersection of two sets is a 5, is a null set, then we say that those two sets are disjoint. So here E and S are disjoint sets. Now look at this relation, A subset of B. We read this as A subset of B, and this as B contains A. So this means that every element of A is in B or is an element of B. So A subset of B or B contains A means every element of A will be element of B as well. Now if we have A subset of B and B subset of A, then we can see that A and B will have exactly the same number of elements, and in this case we say that these two sets are equal, and we write it by A is or write it as A is equal to B. Here we will see one more example. We are defining the set A1 as the set of natural numbers n is equal to 1, 2, 3, etc. A2 we will define as the set of all natural numbers greater than or equal to 2. That means 2, 3, 4, etc. A3 as the set of all natural numbers greater than or equal to 3. That means 3, 4, 5, etc. Similarly, going An is the set of all natural numbers greater than or equal to n. That means set n, n plus 1, n plus 2, etc. So if you look at this, this n is an infinite set, and you can see that A1 contains A2. That means all the elements of A2, 2, 3, 4, etc. are in A1. All the elements of A3 are in A2. All the elements of A4 are in A3, like that. So this forms a nested chain of sets. A1 contains A2, contains A3, contains A4, etc. If you take the union of all these infinite number of sets, that union, that means A1 union A2 union A3 union A4 union, etc., will be in short denoted as union n is equal to 1 to infinity an. That means n varies from 1 till infinity, or you can write it as union n element of capital N, which is a set of natural numbers an. So here n varies over the set of natural numbers. That means n will take the values starting from 1, 2, 3, etc. till infinity. Okay, now if you look at this infinite union, A1 union A2 union A3 union, etc., we can see that A1 contains all the elements of A2, A3, A4 and all its nested sets. So you can see that the value of this infinite union will be A1. Okay. Similarly, the infinite intersection of this collection, that means A1 intersection, A2 intersection, A3 intersection, etc., will be denoted in short as a intersection n is equal to 1 to infinity an, and we will say that this intersection will be empty. Okay, now why is it empty? Suppose that it has an element, there is an element m in this intersection n is equal to 1 to infinity an, and m is a natural number which belongs to this collection. So what this means that m is an element of an for every an in this collection. So that means m is an element of a1, a2, a3, a4 and up till infinity m belongs to this collection. Okay, so m is an element of an for every an. Now we know that m, by the definition of am, we know that m is an element of am, but m is not an element of am plus 1 because am plus 1 is a set of all natural numbers greater than or equal to m plus 1. Okay, so because of this we cannot find a natural number which will be a member of this collection. So the infinite intersection intersection n is equal to 1 to infinity an will be empty. So now we will move on to the next topic, complement of a set. Okay, now here the numbers which we are discussing are the set of real numbers. Okay, so let A be a set which is a subset of the set of real numbers. Then the complement of A, written as like this, A complement, read as A complement, is a set of all elements of R which does not belong to A. Okay, set of all elements of R which are not in A. This set is called the complement of A and is denoted as A complement. Now, there is an important law regarding the complement of sets. That law is called the De Morgan's law, and it says that A intersection B, the whole complement, is A complement union B complement, and A union B, the whole complement, is A complement intersection B complement. Now we will try to prove this law. So this is one law. A intersection B, the whole complement, is A complement union B complement, and this is the second law. A union B whole complement is A complement intersection B complement. Now we will try to prove this first. Okay. Now to prove that two sets are equal, suppose A and B are two sets. Now to prove that two sets are equal, we need to first prove that A is a subset of B, and we need to also prove that B is a subset of A. So two sets are A and B are equal if A is a subset of B and B is a subset of A. We use the same concept to prove this. Now, first we will prove this. A intersection B whole complement is equal to A complement union B complement. So in order to prove that, we have to first prove that A intersection B complement is a subset of A complement intersection B complement. And again, we have to prove that A complement union B complement is a subset of A intersection B, the whole complement. Now, how do we show that A is a subset of B? To show that A is a subset of B, take any element X in A and show that X is an element of B also. So in this way, we can say that every element X in A is also an element of B. So we can say that A is a subset of B. So this is the way to prove that A is a subset of B. Take any element of X in A and show that that X belongs to B also. So here, first we have to prove that A intersection B complement is a subset of A complement union B complement. So to prove this, we take an element of this set, A intersection B whole complement. We take that element as X. So let X belongs to A intersection B, the whole complement. Okay. Now we just going to the definition of complement. X is an element of A complement if X is not an element of A. Okay, this was the definition of complement. Now here, X is an element of A intersection B complement. So this will imply that X is not an element of A intersection B. Okay, so X is not an element of A intersection B means, so the elements of A intersection B are the elements which are common to both A and B. So X is not an element of A intersection B means X is not an element of A or X is not an element of B. Okay, so if X is an element of A intersection B only if it is both in A and B. So it is not in A intersection B means either it will be not in A or it will be not in B. Okay, so X is not an element of A, that means X will be an element of A complement. Similarly, X is not an element of B, that means X will be an element of B complement. Okay, so X element of A complement or X element of B complement. X will be either in A complement or X will be in B complement. So this means that X will be in the union of A complement and B complement. If X is in A complement or B complement, then X will be surely in the union of A complement and B complement. This is by the definition of union. So this implies, where we started is that X is an element, we took X as an element of A intersection B complement. Now we got that X is an element of A complement union B complement. So this implies that A intersection B complement is a subset of A complement union B complement. We mark it as an equation. So here I mark it as equation number 6. You can take it as equation number 1. So we have proved one part, A intersection B whole complement is subset of A complement intersection B complement. Now we will prove the other part. A complement union B complement is a subset of A intersection B the whole complement. For this we will take an element here in A complement union B complement. So X is an element of A complement union B complement. So X is an element of A complement union B complement means by the definition of union, X will be either in A complement or in B complement. Okay. So X is an element of A complement. That means X is not an element of A. And X is in B complement means X is not an element of B. Okay. So X not an element of A or X not an element of B, that means X not an element of A intersection B, because if it will be an element of A intersection B only if it is an element of A and it is an element of B. So here what it says is that X is not an element of A or X is not an element of B. It will be only in one of the sets. So it is not in the intersection of A and B. X is not an element of A intersection B. If X is not in A intersection B, then by the definition of complement, X will be an element of A intersection B the whole complement. Okay. So we have started by saying that X is an element of A complement union B complement. Now what we got is that we got that X is an element of A intersection B the whole complement. So from here we can say that A complement union B complement is a subset of A intersection B the whole complement. Take it as equation number 2. I'm taking it as 7. So from 6 and 7. So from 6 is that A intersection B whole complement is a subset of A complement union B complement, and 7 is A complement union B complement is a subset of A intersection B the whole complement. So from these two equations we can say that A intersection B the whole complement is equal to A complement union B complement. We shall now prove the second rule in De Morgan's law, which is A union B the whole complement is equal to A complement intersection B complement. Now we will prove this in a similar way which we have proved the first one. So here we have to first prove that A union B the whole complement is a subset of A complement intersection B complement. And then we have to show that A complement intersection B complement is a subset of A union B the whole complement. So to prove the first part, A union B the whole complement is a subset of A complement intersection B complement, we take an element in A union B the whole complement. So let X is an element of A union B the whole complement. So X element of A union B the whole complement implies that X is not an element of A union B by the definition of complement. So X is not an element of A union B. A union B, we know that A union B is the set of all elements belonging to A or B or both. So X is not in A union B means that X is not in A and X is not in B. If X was in A or B, then it would have been in A union B. So x is not in A and x is not in B. This implies that x is not in A implies that x is in A complement, and x not in B implies that x is in B complement. So x element of A complement and x element of B complement. So x is an element of A complement and x is also an element of B complement. So this implies that x is an element of A complement intersection B complement by the definition of intersection. If x is an element of both the sets A complement and B complement, then x is an element of A complement intersection B complement. So we have started by taking x as an element of A union B the whole complement. Now we got that x is an element of A complement intersection B complement. So we get A union B whole complement is a subset of A complement intersection B complement. Take this as equation number 3. I'm taking it as equation number 8. Now we will show the other part. That means A complement intersection B complement is a subset of A union B whole complement. So for that, we will take an element in A complement intersection B complement. Let x is an element of A complement intersection B complement. So this implies that x is an element of A complement and x is an element of B complement by the definition of intersection. If x is an intersection means x will be in both the sets. So this implies x element of A complement implies that x is not an element of A, and x element of B complement implies that x is not an element of B. So x not in A and x not in B implies that x is not in A union B. X is not in A, x is also not in B. So it will not come in the union of A and B. So x not an element of A union B. And this implies that x is an element of A union B the whole complement by the definition of complement. If x is not an element of A union B, then definitely x will be an element of A union B the whole complement. So we have started by taking x is an element of A complement intersection B complement. Now we got that x is an element of A union B the whole complement. This means that A complement intersection B complement is a subset of A union B the whole complement. Take it as equation number 4. I have taken it as equation number 9. And from these two equations, 8 and 9, 8 is A union B whole complement is a subset of A complement intersection B complement, and 9 is A complement intersection B complement is a subset of A union B the whole complement. So from these two equations, we can see that A intersection B the whole complement is equal to A complement union B complement.